Thank you, Shaz, for this opportunity uh, to present in CMIP seminar. So I'm Gopika Suresh. I have just submitted my PhD thesis at the CSIR National Institute of Oceanography. Currently, I'm searching for postdoc and job opportunities. And today, I'm going to present our recent paper, which is published in at Future, the drivers of future Indian ocean warming and its spatial pattern in CMIP models. So coming to a bit of basics, we know Earth's climate is undergoing continuous natural fluctuation. So this beautiful figure I adopted from IPCC report. So as you see here, this is a proxy constructed temperature report. So as you see here, after 1850, that is after Industrial Revolution, warming rate and magnitude is increased, and this is highly attributed to anthropogenic climates, as we all know. And 90% of the excess heat is absorbed by the world ocean. Coming to the Indian Ocean warming, the surface of the Indian Ocean has warmed faster than the tropical average since 1950. So these do have large implications because 1/3 of the world population resides in the rim of the Indian Ocean, and Indian Ocean hosts large marine productivity and fisheries, so these get greatly impacted. And the peculiarity of Indian Ocean is the Indian monsoon. This is mainly due to the large air-sea thermal contrast, the land-sea thermal contrast. So changes in the ocean temperature will affect the Indian monsoon, and there will be more extreme events. For example, in the Arabian Sea, which was having very less number of cyclones during any year, but after 1995, the cyclones number increased in the Arabian Sea. This is mainly attributed to the warming of the Arabian Sea. And Indian Ocean is not an isolated region; it do have global teleconnection, so it impacts the globally. In coming to the observed versus simulated warming of historical record, for example, 1900 to 2020, here I'm showing the observation and here I'm showing the CMIP multimodal mean. As you see here, in general, they agree a more warming in the western side compared to the eastern side, but there is a large difference in the amplitude and pattern. So naturally, we blame the models because we have not yet reached in a position to fully reproduce the Earth system as it is. But there are also problems when considering the observations, because in the observational record, here I am showing the hardest 63 trend for 1871 to 2016, and we do have a more warming in the western side, and it extends towards the eastern side. And if you take the number of observation in the early part of the record, we do have more number of observation in a similar path. This may be a ship track. So coming to the point, that is, if you take at the early part of the record, in case of observation, it trends also partly spurious. It's the trend pattern. Coming to model, we have reached so far in models, but we do have still a lot of problem with models, like misrepresentation of processes, biases, and the internal climate variability. So here I am showing the internal climate variability of CSIRO in case of CMIP simulation. So as you see here, I'm showing the trend of CSIRO for two different realizations. So it's showing almost opposite trends to each other. So understanding the underlying processes, what drives the warming or what creates a pattern, this is important to future of model, to improve the model. So I'm interested in CMIP simulation. So to understand what drives the warming in CMIP simulation in case of Indian Ocean. So here I'm showing the historical record for CMIP multimodal mean for 1900 to 2020. So this is the historical changes and this is the future changes. Whatever we see in the historical part, we see an amplification in the future. So this is just for the multimodal mean scenario. But when it comes to different models in the CMIP database, it shows large intermodal diversity. Here I'm showing 3 different models from the CMIP database, and generally they agree more warming west compared to the east, but they do have large intermodal diversity in case of pattern as well as amplitude. So So most of the CMIP model agree more warming west compared to east. That means the eastern warm pole is extended towards the west and in future. So this will affect the circulation as well as precipitation pattern. Here we are not able to see properly the pattern of warming. For that, I am using a different aspect of sea surface temperature, a more contrasted aspect. So this is RSST, the relative SST, SST minus basin average warming. Relative SST is a non-proxy for atmospheric stability. The region warmer than the average, it creates more convection and it induces precipitation and circulation changes. So here I'm showing the relative SST feature changes for the same model. So we see pattern more clearly. So the major focus of this paper is to understand the mechanism driving the amplitude and pattern of warming over the Indian Ocean in CMIP multimodal mean as well as for the intermodal diversity. For that, we adopt a simplified approach and heat budget from Chang'e 2014. So they assume the net surface heat fluxes balances the oceanic processes for future changes. So we disentangle the air sea fluxes components, which is directly related to local SST changes, which is called the feedback, and this is not directly related to the local SST changes, that is called the forcing. So, for example, if you take the latent heat flux, if the SST, if the ocean warms, it induces more latent heat flux released due to the Newtonian cooling processes. So, this is kind of feedback. And if the wind increase over an ocean region, it induces more latent heat flux release. This is kind of forcing. And in case of Chang'e, they have not considered, they have considered long wave down as full as forcing, but we also disentangle this part. We have also disentangled long wave downward component as forcing and feedback, because recent study says that only 5% of this long wave downward increase is directly coming from direct radiative forcing. The 95% is coming from the water vapor feedback, which is directly related to changes in the sea surface temperature. So rearranging this equation, we can formulate an equation for the SST reconstruction, which is mainly coming from the forcing part plus ocean dynamical part divided by alpha. Alpha is the ocean feedback component. Feedback component is showing the sensitivity of heat fluxes towards SST change. And we also linearize to obtain some basin average and RSST equation through this paper. And also we formulate equation for intermodal variance. So here I am testing our new equation for basin average warming and the RSST, that is pattern formation. So versus our direct CMIP simulation. As you see here, we have a correlation of 0.92. That means this works very well. The formula reconstruction of the averaged basin averaged warming and as well as the pattern of warming works very well. So now I go to understand what drives the amplitude of warming in CMIP models, the Indian Ocean warming amplitude. So here I'm showing the components from the formula. So the sea surface temperature is delineated into forcing plus ocean feedback, ocean dynamical component. So from the forcing, we can take different heat flux component. This is after this gray line. So long wave, latent, and short wave and sensible heat fluxes. So this is for the multimodal mean drivers, and this is for the intermodal diversity. As you see here, the latent heat flux, which is a major component which drives the Indian Ocean warming amplitude for multimodal mean as well as for the intermodal diversity. So I try to dig a bit into this, like why this latent heat flux changes in the CMIP simulation. So this can be attributed to wind reduction in the overall Indian Ocean. So due to the weakening of summer and winter monsoon circulation slowdown, as well as the water circulation over the Indian Ocean slowdown in CMIP model, this is due to the global atmospheric circulation slowdown in CMIP model in future. And also we see an increase in relative humidity over the Indian Ocean. So this contribute to latent heat flux forcing changes in CMIP models. Coming to the pattern of warming in Indian Ocean, we identified two different pattern of warming in CMIP model. One is a zonal iodide warming pattern, And another one is a meridional pattern of warming in the Indian Ocean, that is a more warming north and compared to the cooling south. But the leading mode is iodelic warming pattern. So I here plotted different component of the equation, the in the RSST change equation. So from here we can see that this is the ocean dynamical component, which is very similar to the iodelic warming pattern. So that means this is the major contributor to the iodelic warming pattern, and heat flux is trying to dump. So we go more into the dynamics conclusion. Okay. The Indian Ocean warming pattern, we do have two different kind of warming. One is an iodide-like warming pattern, and another one is an interhemispheric SSP gradient strengthening. Coming to iodide-like warming pattern, a trigger mechanism, it can be anything like changes in the latent heat flux over the eastern side of the basin, or due to the weakening of Pacific water circulation slowdown can influence a weakening of Indian Ocean water circulation slowdown. It can be anything like that. A triggering mechanism, a small initial trigger will induce a positive jerkness, positive feedback over the Indian Ocean. So that means a warm in the warming Western Indian Ocean induced more convection over the Western Indian Ocean. It draws more winds from the eastern side. It also influenced the ocean dynamics, a shoaling of thermocline in the eastern side, a deepening in the western side. So this is basically the Jepner's feedback mechanism. So once it gets activated, this is a positive feedback mechanism. This goes on, and this jerkless feedback mechanism also compensates with a cloud short wave radiation negative feedback mechanism, uh, because there will be more cloud in the western side and less cloud in the eastern side. So it changes the short wave radiation, incoming short wave radiation to the ocean, because western side less short wave radiation, and eastern side there will be more short wave radiation coming to the ocean. It tries to balance the jerkness positive feedback loop, but still we do have an iode-like warming pattern. That means we do have an amplified jerkness positive feedback loop in this case. Coming to the interhemispheric SST gradient strengthening, here also a triggering mechanism activates some loops. So the triggering mechanism can be anything like more warming in the land areas than the ocean areas. Uh, for example, the Arabian land and Sahel is warming, as well as the Indian region is warming. So this kind of warming in the land region can induce northern hemispheric warming as well than the southern hemispheric cooling. So a warming in the northern hemisphere and a cooling in the southern hemisphere will activate a feedback loop. The first feedback loop in the southern hemisphere, uh, there will be more pro-equatorial flow, which increase the wind speed in the southern hemisphere. There will be latent heat flux cooling in the southern hemisphere. This cool the southern hemisphere itself. And in coming to the northern hemisphere, there will be strong southerly winds. So it actually reduces the southward transport of dry air by the winter monsoon. So it weakens the winter monsoon, and this warming will reduce the latent heat cooling in the northern hemisphere. So this warms the northern hemisphere. So these two feedback loops activates, and this drives the interhemispheric gradient strengthening. So this is using some statistical correlations. We identified this mechanism. So now we try to test it more dynamically using an OGCM experiment. So we used one CMIP model, IPS, as a example, and we used IPSL um, model because it is mostly similar to the CMIP multimodal mean. And we used IPSC model to force some scenario experiment like wind only or heat only experiment. So from this simple slide itself, it is very evident that the results are consistent, because the IOD-like warming pattern with the wind only experiments, we get more or like IOD-like warming pattern. and that means the wind is the driver. Wind means it contributes to the dynamical part. That means ocean dynamical part is the driver. So here I'm showing the Indian Ocean average sea surface temperature changes. So the full simulation, which is followed by the heat only simulation here. So that means heat is the major contributor towards the Indian Ocean average sea surface temperature changes. That means from the above the slides before, we have seen the latent heat flux forcing is the major contributor, and we have seen that through these simple experiments. And in case of iodine-like warming pattern, here I am showing the thermocline depth. So the blue color is the reference thermocline, and the black color is the featured thermocline. As you see here, in the western side, the thermocline is it's kind of shoaling, and the eastern side it is western side it is deepening, and the eastern side it is kind of shoaling. So this is also showing the effect of ocean dynamical mechanism in contributing to the iodine-like warming pattern in simulation. And coming to the meridional gradient, here I'm showing the different scenario experiment on all experiments. So this is the full experiment, this is heat only experiment, wind only experiment, and some freshwater and non-linear experiments. So as you see here, heat is the major driver for the meridional gradient. That means the evaporative cooling changes in the north and south is the major driver which contribute to meridional gradient formation. So these results are consistent with the simple heat budget analysis. In conclusion, we formulate through this paper a new efficient method to diagnose the surface temperature, warming amplitude, and pattern. And for the Indian Basin average warming, which is mainly driven by the reduced evaporative cooling due to the changes due to the weakening of the surface in both monsoon as well as water circulation, and an increase of relative humidity. The iodine-like warming pattern is mainly due to the amplified positive jetness feedback loop. And there is also in the interhemispheric HST gradient. This is mainly due to the differential evaporative feedback. The stronger winds lead to southern hemispheric cooling, and weaker winds in the northern hemisphere leads to warming in the northern hemisphere. These findings are crucial for improving future climate projection and enhancing predictability. Uh, Thank you so much. You can scan here to read the paper, and you can contact me if you have any questions. And I'm also looking for a postdoc position. You can please contact me. So I'm happy to answer if you have any questions, please. Thank you so much.
Thank you, Gopika. There is one question from Mohammed Amjad in the chat, if you want to try and answer that. Claudia's got a question. You had a hand up, Claudia?
No, I was just clapping.
Oh. Yeah, there's a question in the chat from Mohammed Amjad, Gopika. He asks, is there seasonal or annual winds impact more on IOD changes?
Okay, I'm not really talking about the IOD changes in this. It is mainly about the IOD-like warming pattern in the future changes. So yes, the seasonal winds are mostly impacting this warming pattern, like the weakening of the monsoonal circulations are mostly impacting the IOD-like warming pattern in the summer simulation.